All right, folks, this is my second lecture on electrochemistry, and we are starting with the concept of something called a concentration cell. In a concentration cell, you are carrying out an oxidation reduction reaction, an electrochemical cell, where the anode and the cathode are the same reaction, which is weird. I know I said you couldn't do that. You can't do that under standard conditions, because under standard conditions, your concentration of your solution is 1 molar on this side and it's 1 molar on this side, and that's already at equilibrium, so it's not going to go one way or another. But if you mess with it and you do a setup like this where you've got 2 copper electrodes, you see the copper electrodes here, and you've got some concentrated copper sulfate and you've got some dilute copper sulfate. You can force this to go to equilibrium by having the enough sulfate ions here so that the copper will hop off and make this solution more concentrated, and the copper in this solution will hop on and make this solution less concentrated until it reaches equilibrium. And you can see that this person has set it up so that the wire runs through this fancy voltmeter here, and he is showing you that the electrons are indeed flowing through, and this is a non-professionally done one, so what you've got here is the copper hopping on this side, and that means that this is the, nope, hopping off and hopping on, no, yeah, so let me take that back. The copper is hopping off here and sending its electrons around and through from the left to the right, and the copper is hopping on here, so this is the same direction as a standard picture is done, so that this is the anode and this is the cathode, and because this is not under standard conditions, it does indeed have a voltage, and you can use the Nernst equation in theory to figure out what the voltage would be. Typically, a voltage for under standard conditions, a concentration cell, you'd have 1 molar and 1 molar, and you would end up with 0 volts. But because the concentrations are different, you end up with a small value here, so you can get one. You're not really going to have to calculate one of these. You're going to have to understand the concept of a concentration cell is it's the same thing, different concentrations, and kind of qualitatively figure out which way the electrons are flowing. And the direction that it will flow is the direction that will equalize the concentration. So if we go back to our picture, we need to have this blue stuff hop on and this copper hop off, and that will equalize the concentrations of these two dudes. All right, next thing. Do you remember Gibbs free energy? I know, Gibbs free energy is from last semester, so you shouldn't have to remember it, right? But actually, you do, because the exam is coming up, and Gibbs free energy thermodynamics is one of the big topics on there. So it's actually sort of nice that we pull this back up at the end here. If you remember, Gibbs free energy is the sort of sneaky way of figuring out if a reaction is spontaneous. And the way that you check is you see if it is a negative change in Gibbs free energy, so a negative delta G, it is spontaneous. Something that we've learned about electrochemistry and spontaneity is that positive E's, so positive values for electromotive force, positive cell potentials, are spontaneous. So delta G's are spontaneous when they're negative, E's are spontaneous when they're positive. Why? They must be related algebraically. And they are. Here it is. Bam. They are related algebraically. Delta G, here is our Gibbs free energy. And here is our E of a cell, a standard conditions electrochemical cell. And it's related to also the number of electrons that are being transferred, similar to the use of the N in the Nernst equation. And this big dude, this is F, the Faraday constant, named after Michael Faraday, who was a real big electricity fellow. And the Faraday constant is equal to 96,500. Isn't that nice? I think that's written down on your formula sheet, but you should know that. And what the Faraday constant is the relationship between the units that we use for charge, coulombs, and the actual electron. We think of the electron as having a charge of 1. It does have a charge of 1, but not in coulombs, because coulombs were not set equal to electrons. They were set equal to something much larger. So you've got to be able to convert between how much charge there is on electrons in coulombs and the number of moles of electrons. So here it is, coulombs, which is the regular unit for charge, which I believe is one of the SI units. Coulombs, which is the regular unit for charge, there are 96,500 coulombs of charge per mole of electrons. That's nice. This is going to come up down here in this box in a little while, and it's going to be a new equality, an equality that you have never used before in stoichiometry, and we're even going to do a stoichiometry problem down there, which is exciting because we haven't done that in a while, and it's good to bring that up again near the end of the year. So we're going to do a stoichiometry problem with F, but for now, when you are sticking F into this equation, which relates how spontaneous your reaction is in terms of voltage and how spontaneous it is in terms of joules and Gibbs free energy, the F value here is 96,500 Faraday constant. All right, one thing that's important to note is that this delta G is going to come out in joules. We're used to thinking of delta G in terms of kilojoules because that's how it's listed in that table in the back of the book when you're doing Hess's law and stuff. So just be aware that because of the nature of individual volts in coulombs and stuff, it comes out in joules, not in kilojoules. All right, there you are. Okay. So we've been talking about galvanic cells, which are electrochemical cells that go forward. So in this case, we've got iron and copper, and if you think about iron and copper and which one corrodes more easily, iron does. So in that case, iron is going to naturally function as the anode. Iron is going to be hopping off into solution, sending its electrons across the wire. The electrons come down and they join up with copper ions, and that means that this iron anode is corroding into the solution, and so it will be losing mass. The copper electrode is going to be gaining copper mass as you go on. This is going forwards here. We've got an example of a porous disk, I don't know, that allows the ions to transfer across so that you don't get a big buildup of charge. So that's going forwards. What if you really wanted your iron anode to get bigger and your copper electrode to get smaller? Sometimes you might. It's not going to do that spontaneously though, because we know that spontaneously, naturally speaking, copper is the nobler metal. It's going to be happier being turned into the metal, and the iron will be happier being the ions. And when you compare the two metals, if you want to force it to go backwards, you got to stick a battery in there. You've got to stick a source of voltage that will provide the gumption to make this go the other way. So if you stick a battery into this system, you can force it to go backwards. So what you can do is you can force the electrons to move from the copper to the iron, which is not what it naturally does. So you can make the copper the source of the electrons. You can make the electrons come off of the copper. The copper is being oxidized, so then your anode is on your right-hand side here. The electrons are moving across, they're getting a kick in the pants from this battery, and they're coming down, and the iron that is in the solution is hopping onto this cathode here, is hopping onto this iron electrode. So your iron is now gaining mass, your copper is corroding and losing mass and becoming ions into the solution. The thing about it, quantitatively speaking, is that the voltage for this half reaction is 0.44 volts when it's functioning as the anode, so forward as the reduction, and copper has a positive voltage when it functions as the cathode as an oxidation. As it functions as a cathode as a I need to do this right. As a reduction, yeah, the reduction happens on the right-hand side. So together we've got something like 0.78 volts. There we go. So that's spontaneous, positive 0.78. If you wanted to go backwards, you're going to have to make your iron function as your cathode. So it's going to have to be the reduction, the gaining these electrons here. That's going to be a negative 0.44 volts. You flipped the reaction, you flipped the voltage sign from positive to negative, and you're forcing your copper to corrode. So you're forcing your copper to function as your anode. And so that's going to be a negative 0.34 volts. That means that this cell has a natural voltage or electromotive force or electrochemical potential. They have all sorts of words for this. The volts are negative 0.78. That means it's not spontaneous. It means you got to kick it in the pants. That means you've got to put a battery on it in order to make it go, in order to turn it into where a natural going one is called a galvanic cell. An unnatural one is called an electrolytic cell. So for an electrolytic cell, you're going to have to power it with a battery that gives you a voltage of at least 0.78 volts, because you need to overcome this negative value. So you're going to have to look and read your battery, and if your battery says 0.5 volts, it won't do. If it says 3 volts, then it's quite big enough. It's got excess volts. Woo! It'll go. So anything bigger than 0.78, this battery will make this go backwards as an electrolytic cell. Ding. You may have heard of the electrolysis of water. Let us talk about the electrolysis of water. The electrolysis of water can be carried out, and in fact, let me make this big so I can point at it better. All right, so the electrolysis of water. You've got water in this beaker, and you want water to function as both your anode and your cathode. You want your water to be reduced at one of the wires, and you want your water to be oxidized at the other wire. And so you need to go take a look at your list of standard reduction potentials. What you can see is that water lives here and here. Here's water functioning as a cathode, and here is water. You got to flip this around to get a list of anodes, if you remember. Here is water functioning as an anode going the other way. So water will, when it is functioning as an anode, turn into oxygen gas. You will create some hydrogen ions, and you will give off some electrons. Those electrons will then go over and be used in this reaction, which will be proceeding in the forwards direction. In this reaction, those electrons will be used. Notice this uses 2. This one makes 4. This one is going to go twice, while this one goes once. So this one is going to use the electrons, add those onto the waters. You're going to make some hydrogen gas and some hydroxides. These hydroxides will actually neutralize with these hydrogens, remaking the water that you can then continue to electrolyze. But what you notice is this one going forwards is negative 0.83 volts. This one going backwards is negative 1.23 volts. Let's look at how that plays out up here in our little picture. With the negative 1.23 and this functioning as the anode, you're making oxygen gas. The negative 0.83 and this functioning as the cathode, you are making hydrogen gas. Remember, this is going twice as fast because this is 4 electrons and 2 electrons, so this is happening 2 times. That's why it's neat. You end up with twice as much hydrogen gas as you do oxygen gas, and you're going to have to power this with a battery. That makes sense. Does water spontaneously bubble into oxygen and hydrogen? Nope. It doesn't. You have to power it. So in order to split water into oxygen and hydrogen, you've got to power it. And it's also making sense that you're making hydrogen and oxygen at this ratio of 2 to 1, because in water, hydrogen to oxygen's ratio is 2 to 1. Isn't that cool? One final little thing that you have to know about is that for this to work, the electricity actually has to conduct, which it doesn't in pure water. So you have to pour some random salt in there. Typically, a good salt that they use is sulfate or sulfuric acid or something. So you've got to put an electrolyte in there in order for this to work. None of these ions are going to react because they're not as good of a cathode and they're not as good of an anode as water is. So in this case, water is acting both as the cathode and the anode, the oxidizing agent and the reducing agent. And the overall reaction you can figure out, and the overall voltage is going to be negative 2.06. Ding. All right, and then last on the notes, we've got the stoichiometry type of problem that you might run across. You might run across a problem that says you were running a galvanic cell, or you were running an electrochemical cell, an electrolytic cell. You had it plugged up to a power source or a battery or something, and you were running 5 amps through it for 2 hours. How much copper were you able to get out? They might ask. And you're like, gee, I don't know. Or they might ask the question, you were able to get out 50 grams of copper. How many amps did you run? You are able to go back and forth between the time that it took to run it and the amperage and the grams of metal that you were able to plate out using some of our electrochemical knowledge. A couple of things that you're going to have to use are the definition of the Faraday that I mentioned before, where a Faraday has 1 mole of electrons equal to 96,500 coulombs of charge. You're also going to need to know what an amp is. You may have heard of amps. Amps are 1 coulomb of charge per second. That's an amp. That's what that means. And so that's a measurement of how many electrons are going by over time. And so because I know the Faraday is 96,500 coulombs per mole of electrons, and I know the coulombs per second in the amps, I can figure out how many electrons went by overall. And I can go, oh, well, there's 2 moles of electrons for every mole of copper, and I know that a mole of copper weighs 63.5 grams, neener, neener. So let's see, what are we doing? Silver. How long must a current of 5 amps be applied to a solution of silver to produce 10.5 grams of silver metal? All right. The thing to remember about these is that you're either starting at grams and getting to time, or starting at time and getting to grams. This one wants to get us to time, so we're starting with grams. All right, let's flip over to, do I have this on the black pen screen? No, I don't, but I will. Here, it's up here. All right, so we're starting with 10.5 grams of silver. 10.5 grams of silver. One thing I know about silver is its molar mass. There's 1 mole of silver in 107.9 grams of silver, I think. Let me go check. Yep, that's it. 107.9 grams of silver per mole. And then you go, okay, well, 1 mole of silver. So I was electrolyzing silver, Let me go and see how many electrons that is. Silver, 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 silver. There's silver. Hey, silver. All right, every time I reduce silver, that's 1 electron per silver. Okay, because that's silver plus 1. If it was, for example, iron 2+, you would put 2 electrons per mole. If it was iron 3+, you'd put 3 electrons per mole. But this is 1 electron, 1 mole of electrons per 1 mole of silver. All right, keep it going, keep it going. Mole of electrons. One thing I know about a mole of electrons that is going to get me towards the charge and the amps, etc., is that 1 mole of electrons is equal to 96,500 coulombs of charge. There is a new equality for you. This one is the molar mass. This one is a mole ratio. This is the definition of a Faraday. It's 96,500 coulombs per mole of electrons. Keep it going, keep it going. All right, and then one thing that I know about coulombs is that coulombs per second is amps. Coulombs, this is sort of funky. You don't run into this a lot because you're putting information from the question into the middle of this problem as well as at the beginning. This is a thing though, it happens. You'll be okay. I know how many coulombs per second I was doing. It told me in the problem. Dear coulombs per second, aha, here it is. Coulombs per second. Coulombs per second is amps. So now I'm doing 5 coulombs per second. 5 coulombs per 1 second. That is because in the problem it tells me that I'm using 5 amps. So I'm putting information from the problem in the middle here, which is crazy, but it happens. All right, and then, wait, no, we're done. Wait, are we done? It wants time, right? How long? Yeah, hey, look. It wants time. And so you work this out, you go 10.5 divided by 107.9 times 96,500 divided by 5, and you end up with 1,878 seconds, or if you feel like putting that in minutes, that's 31 minutes. Bam. So it takes 31 minutes to get 10 grams of silver out. That's not bad. Silver's awesome. We want silver, right? So we could just set up an electrolytic cell on some silver nitrate, say, and produce silver. This is my devious plan to make electrons bend to my will. All right. Flip over back to the back, and we can do question 6, 7, and 8. All right. Questions 6, 7, and 8. You go ahead and do 6, 7, and 8 yourself, and then come back and see if you are right. Question 6. What is the value of delta G for the cell from question 4? Ooh, that was from the last lecture. And we didn't know how to do delta G back then. That's why we didn't do 6 yet. All right, delta G. Delta G is equal to negative NFE dot. That is the number of moles of electrons, the Faraday constant, and the voltage at standard conditions, plus the negative as well, because spontaneous negative delta G's are positive E's. So that's going to be delta G is, what question was this? How many electrons? This is the tin and silver, and if we remember the tin and silver balanced equation, that was 2 electrons, so that's our N. So negative 2 times our Faraday constant, which is 96,500, times our voltage, which was, what was our voltage? 0.94 times 0.94, and that gives us a delta G of negative 1.81420 joules, or negative 181 kilojoules. That is pretty spontaneous, which makes sense. We should know that, right? Because this was spontaneous in terms of the electromotive force. It's spontaneous in terms of the delta G. But this allows us to convert units between voltage and joules. Cool, huh? All right. Determine the direction of electron flow and designate the anode and cathode for the concentration cell represented at, well, for me it's on the right. For you on your paper it's on the left. Explain. All right, so here is our concentration cell. We've got some copper, and we've got it in some copper ion solution. Let's say this is copper sulfate, say. Oh, why do we always use copper sulfate? Because it's pretty. And we need to figure out which one is which. We have a concentrated copper here of 1 molar and a dilute copper here of 0.01 molar. So what's going to happen is we need to increase this concentration and decrease this concentration. That's what it's going to do spontaneously. It's going to go to equilibrium where both sides are the same. So for this one to reduce, copper ions need to hop on, and for this one to increase, copper needs to hop off. For copper to hop off, that means it's losing its electrons. The electrons are going that way, and the electrons are going that way. And that makes sense because these electrons will be what is allowing the copper ions to hop on. So this is loss of electrons, that's oxidation. This is gain of electrons, that's reduction. Red cat and ox. This one is backwards. I did that to mess with you. Can you tell this isn't professionally drawn? All right, so that means that the electron flow is going left. The anode is anode. This is the cathode, this is the anode, and explain. I've explained. You've got it. You're good. All right. How many grams of copper will be plated out from an electrolytic cell, delivering a constant 5 amps for 45 minutes through a concentrated solution of copper chloride, copper 3 chloride, copper 3? That's not even a thing. All right. We're going to call that copper 2. I better correct that on your notes. So let's see, we've either got to start with time and go to grams, or start with grams and go to time. Yeah, time. Start with time. Start with time. 45 minutes. Minutes. Seconds. Why do we have to convert to seconds? Because amps is coulombs per second. Ooh, that's a good point. All right, seconds. What do we know about seconds? I know that every second there are 5 coulombs of charge. And what do we know about coulombs? There are 96,500 coulombs in 1 mole of electrons. And moles of electrons. And moles of, what are we talking about? Copper? Copper. There are 2 moles of electrons for every 1 mole of copper ions. And 1 mole of copper is got a mass of 63.55 grams of copper. All right, and I need to actually calculate this. So that's 45 times 60 times 5 divided by 96,500 divided by 2 times 63.55. That gives me 4 point, how many sig figs we got here? Ooh, just 1. 4 grams. No, not like a real exclamation point. 4 grams. Ta-da! 4.44 I got, but I've only given you 1 sig fig for the 5 amps. So there you are. That's that. Thanks, folks.